Bismillahirrahmanirrahim. Mm. Today, I will discuss the covariant derivatives. You are familiar with the partial derivative and ordinary derivative. Covariant derivatives, basically, it is the generalization of a partial derivative. The partial derivative of a vector, basically, it is not a vector. However, if you take the covariant derivative of a vector is a vector. Similarly, if you take the covariant derivative of any tensor, it will be a tensor. So in general theory of relativity, we use the covariant differentiation rather than partial derivative. Okay, so in this figure you can see here we want to measure the covariant derivative of the vector v with respect to u vector. So you can see from this figure v is parallelly transport along the curve, or v is moving, v is parallel transport with respect to u vector. So therefore, what we say, the v covariant derivative, this del actually represent covariant derivative of v with respect to u, it will be 0. So therefore, we say v is parallel transported along the curve C. So let us define the covariant derivative of w vector with respect to u vectors. In this case, you can see w is not parallel transport. So therefore, the covariant derivative of w vector with respect to u at p is defined by this equation. Here we have used the concept of ab initio method. Okay, so this is very important result if you want to know what will be the covariant derivative of this is f into w vector. F is a function, so it will be equal to f into del w u plus f plus w del f u. So it is this del f u actually represent covariant derivative of a scalar function with respect to vector u. So this is actually simply basically directional derivative of the function along the vector u. So in fact it is also known, it is defined as df upon d lambda. So okay, similarly, if we compute the covariant derivative of the tensor product of two tensors, namely A and B. So it will be the left hand side represent covariant derivative of tensor A multiplied by tensor B with respect to U. It will be equal to covariant derivative of A with respect to U, tensor product, tensor B plus tensor A as it is, tensor product, covariant derivative of B with respect to U. There is another important result here, the covariant derivative of vector W with respect to G into U. So, the left-hand side of this equation actually represent the covariant derivative of vector W with respect to G into U vector. Here, G is basically it is a scalar functions. So it will be equal to G into del W U. So therefore, the covariant differentiation of W vector with respect to GU will be equal to G times covariant derivative of W with respect to U vector. Okay, similarly, we have very important result, the covariant derivative of EJ with respect to EI vector. Here it is EI. So the covariant differentiation of basis vector EJ with respect to EI vector, it will be equal to this gamma super K JI EK, where this gamma functions, so gamma super K JI, basically they are known as Christopher symbols. So what is the basic idea how to represent this is very important result. So let us give some explanation of this result. So the position vector of any point, it is represented by vector r is equal to xi plus yj plus zk. So in polar coordinate, spherical polar coordinate, a small is in spherical polar coordinate, the position vector can be expressed by this equation r is equal to r sine theta cos phi I plus r sine theta sine phi j plus r cos theta j, r cos theta k. So this is actually this here I have defined the position vector r in term of spherical polar coordinates. So if we take the partial derivative of this vector r with respect to r, so it represents basically ER, and it will be equal to sine theta cos phi I plus sine theta sine phi j plus cos theta k. This ER is basically, it is a vector which is along the radial line ER. So basically ER, similarly, if we take the position vector, if we take the partial derivative of the position vector r with respect to theta, so it is known as E theta, another basis vector, and it will be equal to r cos theta cos phi I plus r sine theta sine phi j minus r sine theta k. Similarly, if we take the partial derivative of r with respect to phi, it is represented by E phi, it will be equal to minus r sine theta sine phi I plus r sine theta cos phi j. The important thing it is that if we take the partial derivative of ER with respect to r, it is 0. However, if we take partial derivative of ER vector with respect to theta, so it will be equal to cos theta cos phi I plus sine theta sine phi I sine phi j minus sine theta k. So basically we can say the partial derivative of ER with respect to theta is equal to 1 upon r E theta. Similarly, partial derivative of E theta can be proved as E phi. So what is what this result showing? There it is showing that the partial derivative of the ER, E theta, E phi basis vector, they can be expressed as a linear combination of the basis vector. So, this equation, the covariant derivative of EJ with respect to EI is equal to this connection coefficient, Christopher symbol, gamma, super K, J, I, E, K. This is the basic idea. Here, the covariant differentiation of EJ, EI can be expressed as the linear combination of the basis vector. So I will discuss later on how to define this Christopher symbol. Sometimes this gamma super K sub Ji, they are also known as connection coefficients. Important thing is that these connection coefficients or the Christopher symbols, they are not a tensor. So how to obtain the covariant differentiation of vector V with respect to U vector? So here, V vector V can be written as V super J, E sub J. V super J, they are the components of the vector V, and E sub J, they are bases of the vector V. So according to product rule of differentiation, so, we apply the multiplication rule of differentiation. So we first take the covariant derivative of Vj with respect to U, Ej as it is, plus Vj as it is, and the covariant derivative of Ej with respect to U. And as I have told you, since V super J is a function, so therefore the covariant derivative of Vj with respect to U, it will be equal to dVj over d lambda. Ej as it is. And since the vector u, it can be written as ui e sub I. Since according to the property which I have discussed earlier, so vui actually come out from the differentiation, covariant differentiation. So the second term can be written v super j ui del ej ei. So now it is actually covariant derivative of Ej with respect to Ei, and I have explained this covariant derivative of Ej with respect to Ei can be expressed in terms of the Christopher symbols, gamma, super K, Ij, E sub K. So now replace K with J here and J with k here. So we obtain the right hand side as, it becomes vk ui gamma super j ik ej. So therefore, what we can say, the covariant derivative of vector v with respect to u is equal to the right hand side of the last equation. You can see here the covariant derivative of vector v with respect to u clearly shows it is a vector. Similarly, in terms of components of the covariant derivative, the covariant derivative is defined by this symbol left hand side, v super j semicolon I. It means it is the covariant, it is the components of the covariant derivative of a vector. So basically, it will be equal to partial derivative of vj with respect to xi plus gamma super j ik v super k. So this form is called components of the covariant derivative of vector v with respect to u. Or sometimes instead of writing dava v super j dava xi, we say v super j comma I plus gamma j ik. So we represent the partial derivative with the symbols comma I, and the covariant derivative is represented by semicolon I. Similarly, we compute the covariant derivative of one form. Here sigma is one form. We know the one form can be written as sigma sub j theta super j. So again, we apply the multiplication rule of differentiation. So we first take the covariant derivative of sigma j with respect to u theta j as it is, plus the covariant derivative of sigma theta super j with respect to u vector and sigma j as it is. However, u is equal to ui ej. So again, using the property of the covariant derivative uj, we can pull ui outside from the del operator. So therefore, we left with this equation, and we know the covariant derivative of theta j with respect to ei, it will be equal to minus Christopher symbol gamma super j ik theta k. Here we have a minus sign. Therefore, the covariant derivative of one form with respect to vector u is given by this equation. So in simple, the covariant derivative of sigma j with respect to I will be equal to partial derivative of sigma j with respect to I minus Christopher symbol super k ij sigma k. Or sometimes we use also this notation. This symbol actually left hand side, sigma sub del sigma a b means covariant derivative of sigma a with respect to b. It will be equal to partial derivative of sigma a with respect to b minus Christopher symbol into sigma c. So we have seen how to compute the covariant derivative of a vector and one form with respect to another vector u. Similarly, we can define, or we can calculate the covariant derivative of a tensor of type 1, T super A sub B, it is a tensor of type 1. So here the covariant derivative of TAB with respect to C, it will be equal to, the first term is partial derivative, and the second term is basically, it is Christopher symbol terms with respect to A. So, we have a plus term. Similarly, Christopher symbol for the B index, it has negative signs, and it corresponds to one form. So, this is the covariant derivative of a tensor of 1 type. Similarly, covariant derivative of TAB, it is TAB, it is a 2 form. So it is defined as partial derivative of TAB with respect to C minus, we have 2 connection coefficient terms with negative sign. Similarly, the covariant derivative of TAB, T super AB. So it is, 2 vectors, or a tensor of top 2, 0. So it will be equal to first term, partial derivative, and second and third terms has positive signs with the Christopher symbols. So, it is very easy to calculate the covariant derivative of any tensors. Geodesics. Basically, in general theory of relativity, equations of motions are known as geodesics. In terms of geometry, a geodesic is a curve which parallel transports in own tangent vectors. So therefore, we say the covariant derivative of u vector with respect to u vector is 0. So this equation number 6.16a, 6.16a is called geodesic equations. So therefore, according to the definition of the geodesic equation, which I have discussed earlier, it will be equal to dui with respect to d lambda plus Christopher symbols term. Here ui basically, u is a tangent vector. So therefore, ui, it will be equal to dxi over d lambda. So therefore, the first term of a geodesic equation become d square xi over d lambda square plus Christopher symbol as it is, and ui actually becomes dxi over d lambda, and uk will be equal to dxk over d lambda is equal to 0. So, equation number 6.16, basically, they are called geodesic equation. So as I've told you, the geodesic equation, basically they are equation of motion in general theory of relativity, like, in Newtonian physics, equation of motion is F is equal to ma. Similarly, in Lagrangian equation, in classical mechanics, we have Lagrange equation of motions. So there will be, many, there will be many equations. For example, J, for 4 dimensions, there will be 4 equations. Here I is basically, it is ranging from 0, 1, 2, 3. So these are the geodesic equations. Let us learn how to. So, as we have seen, Christopher symbols, they are appearing in, geodesic equations as well as covariant derivative of any tensors. And you will see later on, Christopher symbols, they are also express, they explain, curvature tensor. So Christopher symbols are very important. As I told you, it is not a tensor. So, this is a gamma sub ABC. This is called first kind of Christopher symbol. First kind of Christopher symbol, it is defined by, it is equal to half. So, we take partial derivative of G BC with respect to A, partial derivative of G BC with respect to A, plus partial derivative of G CA with respect to XB, minus partial derivative of GAB Dava XC. So this is the definition of the Christopher symbols. Similarly, the second, if we multiply the gamma DCB from the GAD, so, this D is contract, therefore, this G actually raised D as A. So this is called, second kind of Christopher symbols, which appears in, covariant derivative as well as geodesic equation. So gamma super A sub BC is equal to half G AD, and, we have 3 terms. So this is the definition of Christopher symbols. This is the important result. Gamma super ABC plus gamma super BCA. If we take the sum of these 2 Christopher symbols, it will be equal to partial derivative of GAB with respect to XC. The proof is given in these slides. So this is a very important example, how to compute Christopher symbols for 2-dimensional sphere of radius A. this ds squared basically equal to a squared d theta squared plus a square sine square theta d phi square. As I've told you here, theta and phi are two coordinates. So therefore, the coefficient of d theta square is a square. It means g sub theta is equal to a square, and g sub phi is a square sine square phi. So this is an orthogonal metric. Therefore, g super theta will be equal to 1 upon a square. Similarly, g super phi will be equal to 1 upon a square sine square theta. And g sub theta phi, g super theta phi will be equal to 0, and g super theta phi is also equal to 0. So now, we want to compute the Christopher symbols for this ds square for the metric tensor. So now, actually, we want to compute gamma super A sub BC. We put A is equal to theta. So if we put A is equal to theta, so gamma super theta BC. Again, it has, in this case, since we have two coordinates, it has four components. So basically, according to the definition, since theta A is theta, so d a is must be equal to theta. Otherwise, g uh, theta phi it is 0. So therefore, a is equal to theta, and a is equal to theta, and theta is equal to a. It is equal to half g super theta, and then it is equal to partial derivative of g b theta with respect to xc plus partial derivative of g c theta with respect to b. Here you can see here, since BC basically, it can be any values. It can be B is equal to theta, B is equal to 5, C is equal to, so, there are four possibilities. However, we know, okay, G sub theta is 0. If G, for this term, G, B must be equal to, if it is non-zero, so if B is theta, then, B is theta, so G sub theta is a square, therefore this term actually becomes 0. Similarly here, C must be also equal to theta, so it will be also 0. So therefore, first two terms actually become 0. So therefore, we left with this term minus half G super theta partial derivative of G BC. So now we expand this result. You here, BC must be equal to 5. If B is equal to theta and C is equal to 5, it will be 0. If B is equal to theta and C is equal to theta, it is also equal to 0. So there is only one case when B is equal to C is equal to 5. So therefore we have the Christopher symbols, gamma super theta phi, it will be equal to, it is equal to minus sine theta cos theta. Similarly, we compute other non-zero Christopher symbols. A is equal to D and D is equal to phi. Again, here we have these equations. So you can see here, if B is equal to phi, you can see here the only derivative with respect to theta is a non-zero. So therefore, here, what is going on? Okay. We actually drop the first term here. Why? Okay, okay. So we drop the first term and we left with these two terms. So here we put B is equal to theta and C is equal to phi. We obtain the values of gamma Christopher symbols. So this is the way how to compute the non-zero Christopher symbols. अगर आपको कुछ प्रॉब्लम है तो मुझसे क्लासरूम में आके आप लोग पूछ सकते हैं. So this is very important slides. And now we want to discuss how to compute the covariant derivative of vector v with respect to a. So here the vector v is defined by r square cos square theta er minus sine theta e phi. So according to the definitions, we want to compute the covariant derivatives of v super a with respect to a. So since a in this case we have coordinate r and theta, so therefore so we take these, we carry out this summation. This dummy index is a dummy index, so we rr plus theta theta. So now we will calculate the first term of the right hand side and the second term of the right hand side separately. So according to the definition of the covariant derivative, we have covariant derivative of VR with respect to R to be equal to partial derivative of VR with respect to R plus Christopher symbols term, and similarly covariant derivative of V theta with respect to theta, it will be equal to here. So how to now here the Christopher symbols, they are unknown. So we compute the Christopher symbols for the polar coordinate. So in spherical polar coordinate, ds is in polar coordinate, ds square is basically dr square plus r square sine square theta. In these cases, in polar coordinate, the Christopher symbols are given by these equations. We substitute the value of these Christopher symbols in the covariant derivative of r, Vr with respect to r, and similarly V theta. Finally, we obtain the covariant derivative of Va with respect to A. Okay. So, this is our final result. It is equal to cos theta 3 r minus 1. This is very important. Another example, find the geodesy equation for this cylindrical coordinate. In cylindrical polar coordinate, ds square is defined by dr square plus r square, d phi square plus dz square. So for this case, the Christopher symbols for this metric tensor, the Christopher symbols, the non-zero Christopher symbols are these values. Okay. And this is the geodesic equations. When A is equal to R and B is equal to phi and C is equal to phi. So we have this equation. And when A is equal to phi and B is equal to R and C is equal to phi, we have this equation. Okay, so here, the Christopher symbols, gamma super j ab is 0. So therefore, we have this equation, del square z over ds square is equal to 0. So, it shows we have value of z is equal to a alpha s plus beta. So it represents the motion along z direction is linear. So thank you very much. अगर आपको कोई भी प्रॉब्लम है तो मुझसे डिस्कस कर सकते हैं. तो यहाँ पर मैं वाइंड अप कर रहा हूँ. ये लेक्चर है.